welcome back. I hope you all had a great lunch, had some time to have conversations and find some food. Cryptography and matrix, we all know it from the user perspective, we all love it. But how does it actually work under the hood? Well, today we have Sumner Evans from Beeper here to explain it to us. Please give him a warm round of applause.
Thanks, Andrew. So as he said, my name is Sumner. I'm a software engineer at Automatic, working on Beeper. I work on the platform team. We maintain all the bridges and backend infrastructure, as well as our Go client SDK. End-to-end encryption was one of the things that brought me to Matrix, and I'm sure that it was something that brought many of you to Matrix as well. However, Matrix user experience with cryptography is often confusing. I mainly blame other chat networks for this because they're incompetent. Most other chat networks don't even provide any cryptographically guaranteed security. And the ones that do, they normally do so in a way that doesn't really leave the user in control of their keys. Only a few networks, namely Signal, really provide the user control over their keys, and I would say their UX is even worse than Matrix. So in this talk, my goal is to discuss Matrix's cryptography key infrastructure. What do I mean by infrastructure? This is all of the features which support key sharing and identity verification, but don't actually themselves provide the message security. Okay? You can kind of think of this talk as discussing the UX layer of matrix cryptography. All of the things that we're going to discuss aren't strictly necessary for securing your messages, but without them, it would be a horrible user experience. Let's first talk about what we use cryptography and Matrix for. There's two main purposes. The first one is, as I've already mentioned, message security. We only want the people who are in the conversation to be able to read the messages of the conversation. As an additional benefit of how Matrix accomplishes this, we also get tamper evidence. So if the message gets tampered with by a man-in-the-middle actor, we will know. The second reason for using cryptography in Matrix is identity. We want to be able to verify that a specific device or specific user is who they say they are. And one of the most important aspects of this is that we want to verify our own devices to know whether or not we should share keys with that other device. All right, so let's take a look at what we're going to talk about today. This is a diagram which shows all how these core features are implemented and all the infrastructure which supports them. I know it's probably super overwhelming, but we're going to go step by step through this diagram. And at the end of the talk, you should have an understanding of what each part of this diagram means. Now, it's probably too small for anybody, even in the front row, to read. But I want to start by just orienting ourselves to this diagram. And what you'll see here is that we have two users. We have Alice here in purple on the bottom, and then on the top, we have Bob in blue. This diagram is focused on how we share the mega ohm session from Alice's device 1, so right here. I know, again, you can't really read it. We'll zoom in later. And how this gets shared over to Bob and to Alice's other device. You'll notice that there's a lot of colors here, and that's because the diagram is color-coded. The red nodes represent data that does not leave the device, so these ones here. The green nodes, let's go with those first, is data that can be shared freely and can be on the server, so stuff like this over here. The orange nodes represent data that can be shared with trusted parties or members of the same matrix room. So the mega ohm session, for example, needs to be shared with everybody who's in the room, and then this stuff here can be shared with any of your own devices. And then there's some blue and purple nodes. These represent cryptographic operations. OK, it's important that we don't lose sight of what all of this is for. At the end of the day, we need message security. And that comes from what I highlighted here in orange, which is the Megalom session. We're not going to discuss this in detail today. I wrote a whole article about it on my blog if you want to learn more. And I'll provide a link to both this whole diagram and the article about this, as well as an article that basically says exactly what I'm saying in this talk at the end of the talk. So for now, the thing that you need to know about this Megalom session is that it allows us to encrypt and decrypt our messages. This needs to be shared with anybody who you want to be able to read the messages. So we need to share it with other devices for the other users in the matrix room. So we need to share it with Bob. And we need to share it with all of our other devices. So device 2, as well as where it originated, which is device 1. All of the rest of the infrastructure here in this diagram is to facilitate sharing this Megalom session or verifying that another device should have access to it. Let's move on to identity. Okay, so this was the other core feature in Matrix that we use cryptography for. And the highlighted parts of the diagram provide a cryptographic way to verify devices and users. And there's actually two pieces here. There's infrastructure for verifying our own devices and trusting our own devices. And then there's infrastructure for trusting other users and their devices. So what's all the other stuff? Okay, we have a lot more things than just what I've highlighted so far. This is the infrastructure for sharing the Megalom session around to other devices and other users. So highlighted here in red, we have the Ohm encrypted 2-device messages. Down here in the bottom right, we have key backup, which allows you to back up your keys to the server and then restore them from another device. And then over on the left, we have infrastructure necessary for storing secrets on the server, encrypted by a recovery code. So that's been a quick overview of the diagram. But before we dive into the details of it, we need to take a little detour and discuss some basic cryptography primitives. And then we'll break this diagram down into manageable pieces. I'm going to try to explain the cryptography stuff in simple terms. I'm not going to be mathematically rigorous. That's an entire class. What I'm going to focus on is the functionality that each of the primitives provides. Let's start with encryption. Encryption allows us to make a message that can only be read by another user who has a key. And there's two main categories of encryption schemes. First, we have symmetric. This is where both the encryptor and decryptor share the same key. And that key is used for both processes. So encryption and decryption uses the same key. Matrix uses AES, or the Advanced Encryption Scheme, for all of its symmetric encryption needs. The other category is asymmetric. This is where the encryptor needs a public key, uses the public key to do the encryption, and then the decryptor needs a private key. So the public and private key are related, and the decryptor needs that private key in order to decrypt the message. There's a few variants of asymmetric encryption schemes. Matrix uses elliptic curve cryptography for all of its asymmetric encryption needs. Now, with asymmetric crypto systems, there's actually another thing that we can do, and that's create signatures. The idea is that we use the private key to create a signature, and anyone who possesses the public key can verify that signature. And only the person who has that private key can create a valid signature. So if you don't have the private key, your signature will not be valid, and someone with the public key can determine this. Note, this is signing is the opposite of encryption. Encryption, we encrypt using the public key and decrypt using the private key, signing goes the opposite direction. We sign with the private key, verify with the public key. All right, moving on to another concept that's important, and that's hashes and HMAC. So a cryptographic hash function is a one-directional function which takes an arbitrarily large set of data and then produces a unique fixed size output, and that's what we call the hash. Given the same data, a hash function will always return the same output. This allows us to verify that data didn't change in transit, for example, by some malicious or just straight up incompetent actor. If you hash the same message multiple times, you're going to get the same value. And this is good, but it can also cause, it also opens up an avenue for what's called a metadata attack, where an attacker can use information about the frequency of messages to infer some information about the messages being sent. So to prevent these, we use HMAC. HMAC just adds a secret key to our hash, and how it's added isn't relevant at all, but just know that it makes it so that we are not vulnerable to these metadata attacks. Moving on to another concept that's going to be important, and that's key derivation functions. Sometimes we want to turn a small key into a larger key or a set of larger keys, and that's where key derivation functions come in. For example, we might want to stretch a 32-byte shared secret into 80 bytes for an AES key, an initial vector, and an HMAC key. And so Matrix uses a specific kind of key derivation function called HKDF, which uses HMAC, which is what I mentioned on the previous slide, for the derivation process. And you can continue generating bytes ad infinitum with a key derivation function. The last concept that we need to discuss is Diffie-Hellman key exchanges. Often, we need a way to share keys with both the sending and receiving parties across some unsecured channel, such as the internet. We could just share keys in person all the time, but that's super impractical. You know, Matrix is a global network. That's not going to work, and that's where Diffie-Hellman comes in. It's a method of using public key cryptography to facilitate key sharing. Since Matrix uses elliptic key cryptography, the specific variant that we use in Matrix is ECDH, elliptic curve Diffie-Hellman, and I'm not going to talk about the mathematical mechanisms behind ECDH. It's like abstract algebra stuff that I am not qualified to talk about. But what you need to understand is this main feature that it provides, which is highlighted here in this equation. Okay. So the equation is that ECDH of A private and B public is equal to ECDH of B private and A public. So what we have here is two public-private key pairs. Remember that asymmetric encryption where we have public and private. So A private corresponds to A public, and B private corresponds to B public. And if we have either one of the private keys, all we need is the other public key in order to generate the same shared secret, so K shared. We're going to get the same value regardless of whether or not we have A private or B private, as long as we have the other public key. So for example, we have A private, we just find the B public key. Remember, public keys can be shared around to anyone. So if you have, this is something that we can just share willy-nilly across the internet, okay? But if we just have one of the private keys, we're fine. All right. So let's go back to the big picture now. Recall that I said that the blue and purple nodes represent cryptographic operations. And all of these nodes are things that we just discussed. So again, I know you can't really see it very well, but there's HKDF here, there's ECDH there, AES, HMAC, all of these things are concepts that I mentioned in the previous slides. So now let's discuss how these get composed together to provide features within Matrix. We're going to start by discussing how keys get from one device to another. This process is generally called key sharing. And let's remember that the thing that we're trying to share is this megohm session. Okay? This is the thing that encrypts and decrypts the messages. This is the thing that needs to be shared. There's two ways to share these. The first is encrypted Ohm events, and the second is key backup. Let's first talk about encrypted Ohm events. Okay, so I've highlighted the Ohm events in red here. These are sent via two device messages, and that means that we can send it to specific devices rather than to a whole room. Let's zoom in and see what's going on. All right, so I've gotten rid of all the irrelevant nodes. Hopefully it's maybe slightly more legible. But what we can see here is that, again, we're trying to share this megohm session from device 1 to the other devices in our room. So when we want to send the key to Bob, we use an m.room key to device event, and we encrypt it using Ohm. We actually use m.room key events to send to other our own other devices as well. But for our own devices, we have a second mechanism, which is key requests. So Alice's device 2 can send a m.room key request over to device 1. And then if they're verified, if these devices are verified, then Alice's device 1 can forward that room key back to device 2. I'm not going to discuss, oh, and by the way, these are both Ohm encrypted as well. I'm not going to discuss how Ohm works in this talk. It's already been covered many times. It's basically just a signal double ratchet. But for our purposes right now, it's sufficient to understand that Ohm allows you to send devices messages that are secure and encrypted. So this is pretty good, right? We're able to send keys to all the relevant parties. We can exchange keys between our own user. Why do we have all the rest of this stuff? Well, new logins are the real problem. Say Alice just logged into device 2. And she just finished the verification process, did the QR code. If device 1 is online, she can go ahead and send those requests over to device 1, and device 1 can respond. And this works, but there's probably going to be a lot of keys, because every single user in every single room has multiple megohm sessions. And so device 2 is going to be sending a ton of requests, and device 1 will have to do a lot of work to figure out where those sessions are and send them back over to device. This is especially a problem on mobile devices, because devices can't really do this in the background. It's not something that shows up to the user, so they, especially on iOS, prevent it from running in the background. And even on desktop, if you ever log in and have to do a bunch of key requests, your other machines will be worrying for a little while as it's trying to process that flood of key requests. But it's even worse if device 1 is offline or inaccessible, or you threw your phone into the river or something. In that case, Alice's requests are just going to go into the void and never be answered. So this is even worse. And that's where key backup comes in. Key backup allows us to store keys on the server and then restore them from our other devices, even if those other devices are offline or inaccessible, or even logged out. So let's zoom in on this and see what's going on. Again, I've removed all the stuff that's irrelevant and zoomed in just on Alice and just on this key backup. So in the middle, we have in green the key backup. So this guy here. It's in green because it's public. It can be stored on the server. And in fact, that's exactly where it is stored. Again, we're trying to get this megohm session from device 1 over to device 2. So we're going left to right in this example. Obviously, if device 2 has a new key that it wants to upload, it'd be the opposite direction. But we'll just go left to right for simplicity. Within the key backup, there's two components. There's the key backup version, and that backup version includes the backup public key. The private key is up here. in account data. We'll talk about that later. And then the other thing is encrypted session data. So this bottom part. We have an encrypted session data object for every single one of our backed up sessions. So if you have multiple sessions, you're going to have multiple encrypted session datas. So let's look at how this works. The first thing that you'll note, if you can see it all, is that we use AES on both sides of to encrypt and decrypt the Megome session. And this arrow goes here to the server, and it says ciphertext. We only store the encrypted version on the server. So that's good. We don't want to store the unencrypted version. So AES is used to both encrypt and decrypt the session, and then we store that on the server. But AES needs a key, and it also needs an initial vector. So where do we get those? Well, we get it from HKDF. So that's the key derivation function that allows us to generate bytes from some smaller collection of bytes. But you'll remember that HKDF needs a key as well. So where does it get that key from? Well, it comes from ECDH. So that's that elliptic curve Diffie-Hellman thing that I talked about. And what we'll note is that so far, everything's the same on both sides. So AES gets its key from HKDF, which gets its key secret from ECDH. And then on the right, we have AES, which gets its key from HKDF, which gets its shared secret from ECDH. So everything so far has been the same. Let's look at ECDH a little bit closer. Remember, we need a private key and then the other public key for ECDH to work. And this is where things diverge. Here's the formula again. If we have the private key for A, we need the B public key. If we have the private key for B, we need A's public key. So where do we get the A and B key pairs from for our key backup? The first key pair is that Megome backup key pair that I already mentioned. So we have the public key in the version, and then the private key is stored on the device or in secret storage. But the second key pair is this one down here. It's the ephemeral key pair. It's a new key pair that gets created for each one of the backed up sessions. And it's ephemeral because the private part, here in red, gets discarded immediately after we back up the Megome session. The public key is then stored in the encrypted session data. So this is where the sides are diverging. So again, AES, HKDF, ECDH, that's all the same, but the inputs to ECDH are where things start to diverge. So on the encrypting side, we use the ephemeral private key. So we need to use the other public key, which in this case is the backup public key. For the decrypting side, we use the backup private key. So we need to use the other public key, which is the ephemeral public key. So encryption uses these two. Decryption uses these two. The critical thing here to note is that you need this private key, the backup private key, in order to get to your sessions. If you don't have that, you're not going to be able to decrypt key backup, and it's useless. Okay? Again, we make an encrypted session data object for each one of our backed up sessions. And then in that, we're going to store the ephemeral public key and the ciphertext. That gets wrapped up together, but there's one other value, and that's the MAC. So a MAC stands for Message Authentication Code. It's basically just a hash of the ciphertext that we use to verify that it hasn't been tampered with by some malicious or incompetent party. I mentioned hashing earlier. This is one application of hashing. In Matrix, we use HMAC to generate a MAC. And we avoid the metadata attacks because we have this MAC key. Okay. The convenience thing is that we already are using HKDF to generate random bytes, so we can just hook on to that same HKDF that we used for AES, and then use that as our key for HMAC. So what should happen is that we pass the ciphertext into HMAC, so that then if the ciphertext gets modified or the MAC gets modified, we will know. But you'll notice this is not coming from ciphertext. It says nil. And that's because there was a bug in the original libelm implementation. It failed to do this correctly. It just passes an empty buffer. And so that's been the de facto spec ever since. It has been clarified by me in the spec now, so everyone knows that it does the wrong thing. So really, the MAC isn't super useful. It doesn't really tell you that the ciphertext is the same. So hopefully, in a future version of the spec, maybe once we get signed backups, this will change. But for now, it is what it is. OK. Let's move on to device verification. Remember earlier how I talked about sending the key requests back and forth, how we only want to send, only want to forward keys to devices that are verified, our own devices that are verified? Well, now we have to discuss how to determine if a device is in fact verified. And the answer is signatures. Okay, so that's those asymmetric signatures that I mentioned back earlier, where we sign with the private key and then can verify the signatures using a public key. OK, so I'm going to zoom in on this part. In Matrix, each device has a public-private key pair. OK, so device public key, device private key. To verify a device, what we do is we sign the public key. The public key is used as an identifier for the device, effectively. And when we do the signature, sometimes we also refer to that as trusting a key. So when we create a signature for a key, we actually wrap it up in some JSON and such. But then we create a signature for that, and then that's a trust. We trust that key. So we could just use our device private key to sign all the other devices that we care about. That totally works. It's actually how Matrix used to work, like in the dark ages. But that's super inconvenient. If we log in a new device, that new device is going to have to go and sign every single other one of your own devices. And then all of your other devices are going to have to sign that device. Okay, so it's like an n-squared issue. It's horrible. So what we do is introduce a new user-wide key called the self-signing key, because it signs our own devices. And that's this guy here. So there's a private key and a public key for self-signing. Now, how do we know that the self-signing key is trustful? How do we know if we trust the self-signing key? Well, that's where the master key comes in. We have the master private key and master public key again. And the master key, master private key, signs the self-signing key. So then what we do is we use the device key, private key, to sign the master public key. And then any signatures that are derived from that master key, we will know are valid. And what this does is creates a chain of trust. So the device key signs the master public key, which corresponds to the master private key, which then signs the self-signing public key, which corresponds to the self-signing private key, which signs all the other devices. So along that whole chain, we can use the verification method of our asymmetric encryption scheme to verify those signatures and trust all of the devices. Again, the reason for this is now we have to only trust a single key, the master key, and then all of the trust gets resolved for our own devices. Now, sometimes we want to trust a user. We want to know that all of the devices on their account are actually under their control. So for example, if a new device is logged in, we want to know if they have control over it, and we will know if they have control over it if they've signed it. If, for example, their home server went rogue and signed in a malicious device, or they lost their password and somebody logged in, they wouldn't be able to sign the device still, because that requires doing that QR code dance or emoji dance with the other device. So if the device is not signed, then we'll know that they've been compromised in some manner. So let's zoom in on this. This is the this is the infrastructure for doing that. Let's zoom in again. I've removed all the irrelevant stuff. And we know that the other user has already signed all of their devices using their own self-signing key. So we can use the public key, which is public, it's on the server, to verify signatures. And we know that that self-signing key was signed by their master key. So again, we can use their master public key to verify the signatures. And so if we can trust their master public key, we are going to have a chain of trust all the way from our user to their devices. And that's exactly what we do. We actually introduce a user signing key. So the user signing key signs other users' master keys, and it itself is signed by our master key. Okay, so master private key signs that user signing public key, which then goes and signs all the other keys. This creates another chain of trust. It's even longer. So our device private key signs the master public key, which corresponds to the master private key, which signs the user signing public key, which corresponds to our user signing private key, which signs the master public key of the other user. And then we can use the fact that we can verify signatures, again, with our master public key of the other user. We can verify the signature of their self-signing public key, and then we can verify the signature that the self-signing private key made for their devices using just the public key. So through that, again, we only need to trust a single key, the master key, and then all of a sudden, any signatures that we've created previously for other users, we'll be able to trust them as well. This is like way nicer than having to go to every single user, every single device, and trusting them manually. All right. So that's a lot of keys. Where are they all stored? So again, the green stuff, that's public. That can be stored on the server. Yay, thank goodness. OK, so some of the stuff is easy to store. But what about the private keys? Again, private keys need to remain in the user's control. The specific private keys we care about are key backup, for down over here. We have the device signing key for verifying our own devices. We have the user signing key for verifying other users. And then we have that master key, which signs both of those keys. So what do we do with these? Well, these are actually stored on each of our devices. So each of your devices has a copy of the key backup, user signing, device signing, master key, assuming that the client didn't forget about them, which it seems like clients are very, very good at that on accident. I don't know why. And they can actually be shared around using Ulm two-device events. So we can just share these around using key sharing. But what if you sign out of all of your devices or otherwise lose access to them? Well, that's kind of unfortunate. Luckily, there's a solution, and that is secure secret storage and sharing, also known as SSSS or quadruple S. And this allows you to store your keys encrypted within account data on the server. Okay, so it says encrypted account data. Again, I know you can't probably read it, especially in the back there, but that's what it says, encrypted account data. So let me zoom in on this a little bit. So the key that quadruple S uses is basically just your recovery key. There is a basic base 58 decode and then an HKDF, which happens. Again, that's that key derivation function, which expands the key into more bytes. But the path is direct. We use that AES key to decrypt our keys that are stored in secret storage. So if you lose this recovery key, for example, you're kind of out of luck, right? If you've logged out of all your devices, lose this key, tough, right? There's no way to recover your private keys unless you have some super powerful quantum computer, which nobody has luckily yet. And so that's why it's important that you keep this guy somewhere safe, like a password manager. Beeper specifically has lots of warnings telling you to do so, and then our users still ignore it. But that's why it's important. If you lose all your devices and lose your recovery key, all your messages are going to be encrypted forever. So what about this bottom part? So this bottom part is, it's actually not necessary for the encryption of the stuff in account data. What it is necessary for is verifying that your key, your recovery key, is correct before you try and decrypt stuff. I'm not going to go into the full details of this in this talk. You can read the blog post if you are interested in learning more. But like I said, it's not strictly necessary for decrypting, but you definitely should, use this to determine whether or not your device, your recovery key is in fact the correct one. All right, so let's go back to the overview. We've now talked about every single piece of this diagram. We've talked about the mega session. That's this orange thing here that gets shared around to all the devices that are in the room. We've talked about 2 device events, which are used to share that around to other users and other devices. We've talked about key backup, which is a way to store those mega sessions securely on the server and then restore them from another device. We've talked about self-signing of devices, which allows us to verify our own devices using our user signing key, or sorry, self-signing key over here. And then we've talked about signing of other users using that user signing key, which signs other users' master keys. And then we've also talked about the master key, which again signs those user and user and self-signing keys. And lastly, we talked about this part over here, quadruple S, which allows us to store our private keys on the server so that we can restore them if we log out of all of our devices. So this has been a whirlwind, I know, but my hope is that this presentation has helped you understand how this all fits together. My goal is to convince you that matrix cryptography isn't scary. It's complex, it's very complex, but it's not inaccessible. This is something that I think that if you have access to underlying cryptography primitives like HKDF, AES, those sorts of things, it's something that a security conscious programmer could implement. You almost certainly should not be implementing like AES yourself, though. Don't do that. But composing them together is, I think, something that is doable and reasonable, especially for SDK developers. And with that, I'd like to thank you for listening. You can scan that QR code. It has the blog post associated with this talk, and the slides are there as well, including this diagram. So for those of you who had pictures, maybe delete those because they're probably really bad and use the actual one from the blog. Thank you.
Thank you so much, Sumner. All right, if anybody has any questions, please raise your hand. And if you're watching the stream, you may ask them in the Matrix room.
Hey, phenomenal talk. I learned a lot. Thanks so much. I had maybe a potentially dumb question. From the client perspective, like implementing a client, what are some pitfalls or mistakes that we could make? Like, would it be wrong for us to store any of these things in, non-secret storage and like outside of the OS keychain, in standard memory or files?
Sure, yeah. I mean, the biggest thing is just general security practices, not following them, right? That would be the biggest issue. Like you mentioned, storing it in some unsecure place would be a bad idea. In general, if you're on a mobile device, you have a sandbox, so it's pretty safe to just store the keys in the sandbox. Honestly, a big thing is just forgetting to do signatures, or that's a big pitfall. I'm guilty of that, done that a couple times. Or failing to, like I mentioned, for some reason, clients just forget about these private keys all the time. I don't know why. And it's really annoying. So stuff like that is important to keep track of. And personally, I think it's good to know this kind of general architecture. Even if you use a library that provides all of this, at least you know what you need to store, and you know, like, oh, this is actually important. I feel like some SDKs are a little bit too black box on this, and then if you think that you don't need to implement something, it turns out that it's actually super critical, and that can be problematic.
Thanks. Just quick follow-up, just to distill that into something even stupider and more simple. To use color coding here, the yellow recovery key, obviously, that's user maintained, so not a concern. So all the orange things here are things that should go into secret storage, or whatever you want to call it.
So the Megalom sessions, you can just store those on the device. Like, they don't have to go into the secret storage in account data. They get uploaded to key backup via the key backup mechanism. But really, the four keys that matter, that you need to store on the device in a secret place, and then you also need to upload to account data via the encrypted account data mechanism, is the user, self, and master key, and then the key backup key. There's a ton of these Megalom sessions floating around, because every single user, every single device, every single room that's encrypted has one of them. And actually, they have multiple of them. It gets rotated every 100 messages. So these just use key backup to save them. Make sure you do that so that then other devices can restore from them, and not have to request the keys. But yeah.
Okay, so I have a question on the client side. On the Element Web, there's a button called Reset Backup. And I have a question that what is the supposed behavior of this button when you click the reset in a device that already have the message and data? Should it preserve the message or not?
So I'm not an Element dev, but I'm going to do my best. I think that what it does is resets all of this encrypted account data stuff. So theoretically, all your messages should still be able to be decrypted if you have them on the device already. If they're in key backup, they're lost because you just reset your key.
Exactly. So it should like preserve all of the message when the
theoretically. I don't know if it actually does.
Yeah,
again,
that's
I'm not an Element
It's
dev.
a bit like
like
unstable in that sense that sometimes I do the reset and the message is preserved, but sometimes it's not.
Yeah.
So
and some of that I have no idea.
All right.
It's not a code path that we want you to use, because like ideally it just never has to get reset. Just don't lose your key.
Yeah, because sometimes people don't use security key, but they use a passphrase. So sometimes they
and actually I didn't show that, but the passphrase is basically just like another transformation to get to the recovery key, and then it's the same
so
deal.
Because of that, but the passphrase is something that people want to remember. So sometimes they want to change that so that they can still remember that.
Yeah.
And that's the use case that people want to do the reset sometime. And
I would say so kind of to that point, I think that there's probably some room for making resets a little bit more granular, so that you aren't resetting the entire thing, and maybe just resetting like certain parts. But that's beyond my pay grade.
Okay.
So yeah. Other
thanks
questions?
anyway.
Anybody else? We have one quick question from the room from James Riley. Is it possible to shove the entire secure backup key and password on a YubiKey?
Probably. I don't know. I haven't tried.
Somebody in the audience has said no. Would you like to speak to that?
Not currently, but maybe try it. It won't work well.
Nope. Yeah, it's just a password, so you should be able to put it on a security key, but I don't think anyone's tried it, so please do. We had one more question at the front.
So is there any functionality with regards to key revocation or superseding keys, or are you expected to just every time you, for example, log out from a device to completely restart the bootstrapping of the encrypted account data and so on?
Key revocation, I don't really know. Like there's no like timeouts or anything. There's not really any clear way to do that. Obviously, you can just there may be a way to delete signatures. I'm not entirely sure, but that's something I don't have anything insightful to tell you about, unfortunately.
Okay, last question.
I just want to follow these questions. I have a talk in the very end of it, which I hope to at least discuss and answer some of those questions. So welcome to join that session.
And your name is Wenjing. All right, that's all the time we have for questions. Thank you, everybody. Please give another round of applause to Sumner.